Hello everyone, my name is Javier Naranjo-Alcazar and I'm going to explain our submission to the DCASE 2021 edition Task 1B. The presentation will consist of the following points. First, the concept of acoustic classification will be introduced. Next, the goals we are trying to achieve in our work will be explained. Then, we will show the system we have designed and the results obtained. Finally, we will compare our system with the other submissions and some conclusions will be drawn. Acoustic classification is understood as a specific task within the field of machine listening. The ultimate goal of the acoustic classification task is the labeling of an audio, usually of a duration of 10 seconds in a predefined scene. This task has attracted a lot of interest from the community over the years, and many solutions have been proposed over the years. For example, different two-dimensional audio representation, different ensemble techniques, or data augmentations. The objective of these editions can be understood as the following. The core objective is to improve the accuracy of the system by using visual data from the scene. Unlike subtask 1A, this subtask has no limitation on the complexity of the model, understood as the number of parameters. However, the intention of this team is to maintain a trade-off between the system performance and the system complexity, as ideally this system could be deployed in an IoT device in a production environment. The system implemented by this team consists of two modules. The module that is trained with audio data and the module that is trained with visual data. In the experiment sections, the results of each module will be shown independently, as well as the result of both modules working together. The audio module follows the approach that this team has presented in the previous editions. The audio is first transformed into a two-dimensional three-channel representations. These channels correspond to the left channel, the right channel, and the difference between the two. The two-dimensional representations correspond to the spectrograms obtained with the MEL and gamma tone filter banks. As will be seen in the experiment sections, the gamma tone filter bank shows the better performance. As in these editions, the prediction has to be done for each second of the audio. The input to the network corresponds to a spectrogram of 6453 shape. The network is composed of standard post blocks. These blocks correspond to the residual blocks incorporating squeeze-excitation techniques. These models were proposed by this team. After each block, dropout and max pooling layers are implemented to prevent overfitting and reduce the dimensionality of the input as the number of filters increases. Before the classification layer, a global average pooling layer is implemented. With regard to the visual module, the great work done by the community in this field over the years has been built upon. Thus, a network trained with a BGG architecture, specifically BGG16, has been used with the Places 365 database. The convolutional layers remain frozen and have only been modified with the addition of a time-distributed layer. For the extraction of temporal features between 5 frames per second, GRU recurrent layers are implemented before the fully connected layers. These layers are the ones that are actually trained to the dataset provided in the challenge. The complete system can be seen below. The top branch corresponds to the visual model and the bottom branch to the audio model. These models are trained individually. Once trained, a training is carried out with layers in charge of merging the information of both modules. This merge is performed in two different points of the network. The first one corresponds after the convolutional layers of each module. The fusion of both modules generates a representation of 640 features. These feeds are bidirectional GRU layer from which a prediction is subsequently extracted. This point is known as the early fusion prediction. This new prediction, together with the ones of the individual modules, generates a new prediction, known as the late fusion prediction. As mentioned above, the modules are trained independently. Regarding the visual module, only the recurrent layers are trained. Once trained, these weights are frozen and the function layers are trained. When this training is finished, All weights are unfrozen again, and the network is trained with a very small learning range to further improvements. As can be seen, the maximum number of epochs is 200. However, some callbacks were implemented. The batch sizes corresponds to 32 and 16 depending on the system. The networks were trained with data of 1 second duration. As for the audio module, the mix-up technique was implemented so that the network could generalize better. One thing we would like to point out about our system is its complexity. As it can be seen, the trainable parameters of the system are less than 300,000. Ideally, this solution should be deployed in IoT devices. Therefore, the simplest possible solutions are required in order not to saturate the device. The results obtained are as follows. Regarding the audio module, the representation based on gamma tone filters performs better than the one based on MEL filters. On the other hand, the visual module shows a high performance with 87% accuracy in the development stage. The fusion of both modules improves the performance of the system as intended in these tasks. It improves the accuracy by 2% when the fusion is performed at an early stage and by 3% when it's performed at a late stage. The three systems submitted to the challenge were the audio module based on gamma tone filters, the visual module, and the multimodal system with a late fusion. This last system scored 86.5%, 3.3% higher than the visual module. If a class-by-class analysis is performed, we can see that almost all of them benefit from the complete system. If a comparison with other participants is carried out, it can be seen that our position was the 7th. Only 7 teams obtained a result above 85%. The team that played sixth saw a 88.5% accuracy with 140 million parameters. All the systems above the 90% accuracy had at least 40 million parameters. Our system had 15 million parameters, less than half. The conclusions drawn for the work are as follows. Our system fulfills the final objective of the task. A sync classification system is performed using 2 sources of information. The systems can be used independently and subsequently merged with different techniques. Moreover, the proposed system presents a high complexity performance trade-off. The idea to working on the future is to reduce even more the size of the models. That's all. I hope you found it interesting and don't hesitate to contact me if you may have any question. Best regards.